I'm with Mark Greaves, and we're up in Snowdonia. Hi, Mark.
Hello.
Now, Mark is an employee of the Ordnance Survey.
That's right.
What's your job description, Mark?
My job title is Geodetic Analyst. In a day-to-day sense, that means I'm responsible, along with another colleague, for the Ordnance Survey's network of permanent GPS receivers. We have 110 receivers spread around the country, and essentially they're the replacement for the traditional trig pillars that you used to see on tops of hills. Those pillars are now redundant for surveying purposes, and instead we use this network of permanent GPS stations to both monitor movement of the country, but also, more importantly, produce a correction service for our surveyors, because all our surveyors use GPS, and to use GPS accurately in real time, you have to correct the errors from it. So our base stations generate that correction signal, and we send that to our surveyors. So on a day-to-day basis, that's my main responsibility is that GPS network.
Now, concerning the base stations, they've been there for many years, haven't they?
Some of them have. Some of them are fairly recent. We've recently, very recently, finished building the network. In fact, there are I think 3 builds left to do. A couple on the west of Scotland and one in the Scilly Isles. The tripods are in place and waiting for communications connecting. But yeah, some of the stations have been up for over 10 years. One on headquarters in Southampton, for example, is I think nearly a decade old, and there's one or two around the country that have been there for quite some time.
And the accuracy and position and height?
We've recently just recomputed the entire network, connected it to highly accurate stations in Europe, and the accuracy of that computation horizontally was 2 millimetres and vertically was between 6 and 7 millimetres.
And how many people are there with your job description based at the OS?
Because there's two.
There's
There's myself and another colleague, so we work as a very small team.
Yeah. Now, of course, the OS offices down in Southampton are going to be moving shortly, aren't they?
Yes, that's right. Next few months.
And you've told me before that you work from home?
I do. I live in West Yorkshire, halfway between Keighley and Skipton. So I'm very lucky in that I can work from home.
But you have a colleague of the same job description based at Southampton,
Yes,
I believe?
I do, yeah.
Yeah.
And we use technology to keep in touch, instant messaging and video conference, and I physically go to Southampton once a month.
So would you think that, Paul, if I said that you were one of the UK experts on GPS, would that be correct, do you think? You're probably too humble to admit.
Maybe. Certainly within Ordnance Survey, myself and my colleague are the GPS experts, and whenever there's a GPS problem or a question or a solution that needs designing, then we're the people that they come to.
And of course, what you're dealing with is computer models an awful lot, aren't you?
Essentially, yeah. Most of my day is spent in front of a computer, either dealing with GPS processing or the tasks associated with it.
Well, this is the time where you need to bedazzle me with science and technicalities. If you can just sort of explain exactly, what you sort of go through, the different modelling involved.
Well, in the GPS data that we get from the network. Well, to provide a correction signal to our surveyors, it essentially relies on the fact that we know where the stations are very accurately. Because the station position is known, then you can look at the signal, and the signal will give you one answer for the station position, but that will have errors in it. So because the positions have already been predetermined very accurately, you can kind of work backwards and use that information to work out the errors in the signal. And those errors are all collated on a set of servers in Southampton. And the end product is an error correction model for GPS for the entire country, and it obviously varies depending on location. So when one of our surveyors in the field is wanting to use GPS to accurately survey a new road, for example, he will start his local kit going. He has a little backpack and an antenna on a pole, but then he also has to connect, usually via mobile phone, to the servers in Southampton and obtain this correction signal, which is tailored for his specific location. So on its own, his GPS will only be accurate to a few metres, but once we add in the correction signal, it then becomes accurate to a few centimetres, which is obviously accurate enough to to make a map and to survey a road or a house or whatever feature it is that is put in on the map. So the correction involves computing the influence of the atmosphere on the signal, the troposphere, the ionosphere, and various other kind of earthbound effects on the signal as well. The oceans produce an effect where the tides come in, it actually presses the land down, and the tide goes out again, the land goes back up, and you have to model that. And anything that's going to affect the signal and the position of the stations has to be removed and modelled.
And of course this technology, it's widely used, isn't it, by different organisations in Britain?
It is, yeah, for various reasons. The Met Office also take our data because, again, knowing where a station is and the fact that the GPS signal passes through the atmosphere and specifically the troposphere, which is where quite a lot of humidity occurs, you can actually calculate the amount of humidity in the troposphere, which is very useful for weather prediction, and I think the Met Office feed that information into their numerical weather models, and it's very helpful to predict the weather.
And other practical uses, Mark?
Well, for high accuracy GPS, most of the practical uses, apart from national positioning and things, are kind of geological and geotechnical, things like monitoring plate movements and things like that. And you could, with a sufficient amount of GPS receivers, you can monitor ground movements sufficiently accurately to I wouldn't say predict earthquakes, but to certainly research earthquakes and to try research earthquake probability. And you could also use GPS on volcanoes, for example, to try and measure if a volcano is about to blow its top, because it will bulge out prior to blowing out. So you could stick enough GPS receivers around the volcano to measure that bulge to within a few centimetres, and hopefully give some advance warning that the volcano might be able to erupt. So. And
the future for the technology, because it is ever advancing, isn't it? There's various models that what you were talking about before that people can use. But what do you think that because the practical use that many people use on an everyday purpose, for hill walkers, GPS units handheld, and also for many travellers it's sat nav in a car, isn't it? But where do you think the future sort of holds? Firstly, for those sort of uses, that everyday uses, and secondly, any more advances expected in accuracy?
I think for the everyday use, there's new constellations. There's a Russian constellation which is used in surveying GPS, but is not really used very much in consumer GPS. But there's the new European system, Galileo, which in a few years' time will be live. And using GPS and Galileo together, particularly also GPS is itself being modernised, so that in 6-7 years' time, both Galileo and GPS will be more accurate for general civilian use. So your sat-nav will be more accurate, and it'll be more reliable even when you're in a big city, classic urban canyon with a very small view of the sky. There should still be enough satellites up there to get a good fix to tell where you are.
And for everyday use?
Well, that is really for everyday use. But for the more scientific use, again, the extra constellations just mean more observations and more accuracy, more opportunity to model the last few errors that stubbornly stay in the signal and get even better accuracy from the results.
Well, Mark, it's been very interesting, been highly technical, but it's a subject, Mark, that I greatly appreciate you giving your time today.
Okay, nice location to do it.
It's lovely, isn't it?
Seagulls soaring past us.
Yeah, gorgeous afternoon. So, Mark Greaves, Geodetic Analyst at the Ordnance Survey, many, many thanks.
Thank you very much.